If we consider an elliptical trajectory of a planet that's orbiting the Sun occupies one of the two foci of the ellipse. According to classical non-relativistic physics, or if you want Newtonian physics, a planet traces out an elliptical orbit that's fixed, doesn't change. But according to general relativity, there is some correction to this. And you can see here in this sketch that after each revolution of the planet, the elliptical orbit is rotating together with the planet. So after one revolution, there is an angle delta phi, that's causing a shift of the aphelion here, but also the perihelion here. In particular, in the 20th century, the theory of general relativity was used to calculate this delta phi for Mercury because it is much more evident, and this effect did manifest itself even before general relativity, and astronomers and physicists were not able to explain this. It took Einstein to explain this phenomenon, and it was accurately described by general relativity. Here's an animation of the trajectory of a planet around the Sun, where you can see this kind of relativistic phenomenon magnified or accentuated, let's say. You can see that after every revolution of the planet around the Sun, there is a shift of the elliptical orbit. This is of course exaggerated because it is much less visible than it is here, because this effect takes many centuries to manifest itself. The corrections are quite small, but can still be observed. The second phenomenon that we will try to explain is this, the bending of a light ray under gravity. In particular, here you can see a star that occupies this actual position here, and this star emits some light rays that can be observed by an observer located here on the Earth, but the observer sees the star located there instead of there because of gravitational effects caused by the Sun that's bending light rays. And here you can see the angle which a light ray passing very close to the Sun is deflected by, and we can calculate this angle ourselves. We will find the formula that I have written down here on the right. We have 4 times the gravitational constant times the mass of the Sun, or in general the gravitational source, which can be the Sun but can also be another planet. Here you have the speed of light squared. Here you have the shortest distance of the light ray from the gravitational source. In this case it's the Sun. If we consider a light ray skirting the edge of the Sun, we can use this number here for rho. This is approximately the radius of the Sun, 7 times 10 to the 8 meters. So I'm using the International System of Units, so you can insert the constant g, you can insert the mass of the Sun here, 2 times 10 to the 30 kilograms, speed of light in meters per second, and then you have to square it. You will get this number. It's a very small number in radians, and this number can be converted to arc seconds. So we will define arc seconds in the course, but you just have to multiply the result by some factor and you will get another number here. The notation for arc seconds is these 2 apostrophes that you can see here, and you can see that this number is exactly this one here in this picture. And finally, we will assume that we are in a weak gravitational field, and from the weak gravitational field we can derive from Einstein's field equations a wave equation that's satisfied by the metric tensor, and this perturbation propagates with the speed of light, and it is a wave.